4 awesome ways to find matrix inverse I fell in love with. Okay, and these ways are first of all by finding adjoint of a matrix, which is actually the most common way, but it's simple and it's elegant, right? Next is like Gauss-Jordan method. It's also pretty common, but these last two, Cayley-Hamilton theorem and Neumann-Series, are like just awesome and brilliant. And I'm pretty sure you're gonna love this too. Like if you haven't ever seen some like unique ways of finding matrix inverse other than like by finding adjoint or Gauss-Jordan method, you're gonna be completely surprised by the third and the fourth method. They're so good. Okay, so let's start. And for the sake of easiness, I'm gonna choose 2 by 2 matrix, right? And that 2 by 2 matrix is also I have already chosen, and it seems a bit complicated, but the reasons for me choosing this matrix will be obvious a bit later on. So yeah, I'm choosing this matrix to find inverse for throughout the video. Okay, -1/2, 1/2, -5/2, 7/4, right? And actually, we also know I already know it's inverse, so that it will be easier to take our answers, right? Its inverse is 14/3. Sorry, 14/3, -4/3, -4/3. Sorry, -4/3, 20/3. Okay, so let's first go by the first way by finding adjoint, right? And again, to find adjoint, you need to first find the matrix of minor, matrix of cofactors, right? Okay, so to find minor of A, what you do is like you make a matrix, right? So what you do is corresponding to every element, you cross out the row and column of that element and find determinant of remaining entries. So remaining entries is the 7/4 over here, and it's one dimensional, so it will just be 7/4. Similarly, if you cross out the row and column of 1/2, you will have -5/2, right? If you cross out the row and column of -5/2, you will have 1/2. And for 7/4, you will have -1/2, right? Okay, that's the first step to find minor. Yeah. And now after that, we find cofactor matrix of A. To find cofactor of A, what we do is we go on placing negative sign in checkerboard pattern, right? So the first one won't have negative sign, second one will have negative sign, third one, this one will have negative sign, and this one won't have, right? So it's in checkerboard pattern. And so it will be 7/4, right? And then 5/2, -1/2, and then -1/2, right? Yeah, 7/4, 5/2, negative. Okay, yeah, good. Now and then we find adjoint of A, right? So to find adjoint of A, you just take the transpose of cofactor matrix. So this becomes 7/4, 5/2, -1/2, -1/2, right? So that's the transpose. And then after that, to find inverse, okay, you firstly determinant as well. Determinant of A will be equals to -1/2, 7/4, -1/2, -5/4, right? 2 into 2, it's easy. Like the first diagonal minus the product of second diagonal, right? And this is -7/16, minus this is 5/8, right? And that becomes it's like, is it -17/16? That seems to be a pretty big number. Let me just recheck. Okay, the determinant is -7/8. Okay, this is actually plus. So the I see there. Okay, this is actually becomes plus. So that becomes 3/16. I think that's fine. 3/16 is fine, I guess. Yeah. Okay. So I just found determinant using the formula like A1. I mean, this is product of the first diagonal minus product of the second diagonal. That's one true for 2 by 2 matrix. For 3 by 3, it's different, and yeah, you just have to look it up somewhere, right? Okay, so I again have a mistake over here. Actually, that's why I was waiting to see if there's any problem or not. Okay, how come I missed a lot of things over here? Like both the things are wrong. Okay, minus 7 over 8. Wait. Okay, wait. Negative 1 over 2, 7 over 4 minus 1 over 2 minus 5 over 2. Okay, that's right. Negative 7 over 8 plus 5 over 4. Okay, now that's good. So now this is 10 minus 7, which is 3 over 8. Okay, now that's finally fine. Okay, then after that, what you can do is to find inverse, that will just be 1 over determinant of A times adjoint of A, right? And that will now be 8 over 3 by 7 over 4 minus 1 over 2, 5 over 2 minus 1 over 2, right? Now if you multiply, this will be 14 over 3, right? And then next will be negative 4 over 3. And then this will be 20 over 3. And then negative 4 over 3. Yeah. Okay, that gives us the answer, right? Okay, so this is the first way, and this is the most common way. First find minor, cofactor, adjoint, determinant, and then you get the inverse. And this is what it is. Now, next one. Next way is actually pretty nice. So what we do is, we first write the matrix, right? Okay, okay. Let me just copy this first. Copy, and then paste over here. Okay. Okay, we first just write the matrix, right? Minus 1 over 2, 1 over 2, minus 5 over 4, sorry, 7 over 4. And side by side, we write unit matrix of the same order, right? And what we do is we go on performing the row order, row operation, so as to transform the first matrix into unit matrix. And when the first matrix transformed to unit matrix, at that point, this would have transformed to A inverse. So it's based on the idea that every row operation is kind of multiplication, right? So the thing that multiplied with this matrix to give it unit matrix should be the inverse, and the inverse that multiplies to the identity matrix should be inverse, right? So that's how it works. But yeah, let's use this away. So first of all, what I'll do is I'll just multiply row 1 by negative 2 row 1, right? So that to make the first entry just 1 and then negative 1, it should be negative 2, 0, and then negative 5 over 2, 7 over 4, 0, 1. Let me also multiply, okay, for the sake of easiness, let me multiply second row by 4, okay? That it will be easy to deal with things later on. 1 minus 1, minus 2, 0. Now this is minus 10, 7, 0, 4, right? Okay, now I can try to eliminate things. So row 2 to be row 2 plus 10 times row 1. That gives me 1 minus 1, negative 2, 0. So this is 0, negative 3, negative 20, and 4, right? Is that good? Yeah. Oh, no, it's not. It's, wait, it is. Okay, 10 times. If I had 10 times, negative 3, yeah. Okay, yeah, I think it's good. Okay, yeah, let's go ahead. And now after that, I just divide this row 2 by 1 over negative 3. That gives me 1 minus 1, negative 2, 0, 1, 0, 20 over 3, negative 4 over 3, right? Now again, I have to eliminate that minus 1. So I will do row 1 to be row 1 plus row 2. That gives me 1, 0. And that will be 14 over 3. That will be negative 4 over 3. And then 0, 1, 20 over 3, negative 4 over 3. And yeah, now since the first matrix is identity matrix, the second matrix over here will be the inverse, right? And it's exactly the same thing. Yeah. So in this way, we find that inverse to be 14 over 3, negative 4 over 3, 20 over 3, negative 4 over 3. So this is how we get the inverse by this second way. Okay, which was Gauss-Jordan method, right? Gauss-Jordan method. First one was just adjoint method. Okay, the third one is so interesting, guys. Third one is just awesome. You guys will love it. I'm pretty sure about that. okay, Cayley-Hamilton theorem, right? And you can also say it as using annihilate annihilating polynomial. Okay, third one, using Cayley-Hamilton theorem or annihilating polynomial. Annihilating polynomial. I'll tell you what this is when the context arrives. Okay. First of all, what we just do is we try to find its characteristic polynomial, right? So let's find that out. So what you can do is you just take determinant of I lambda minus a to be 0, right? And now I lambda minus a turns out to be lambda plus 1/2, right? I guess you guys know how to do this. Let me do it step by step. So lambda 0, 0, lambda is I lambda minus a is negative half, negative 5/2, 7/4, right? And determinant should be 0. So this becomes determinant of lambda plus half minus half 5/2, right? Minus half 5/2 lambda minus 7/4. This determinant should be 0, right? So now if I do determinant, this will be lambda plus half, right? And then lambda minus 7/4 minus yeah 5/2. Guys, let me notice. Okay, wait, just a second for me. Okay, I don't think that's a problem. Yeah, okay, that's good. I'm sorry. Okay, 5/2 minus 1/2 is equals to 0, right? Yeah. And now the polynomial becomes lambda square minus 7/4 lambda plus lambda/2 minus 7/8 plus 5/10 is equals to 0. Wait, 5/4, sorry. Guys, why do I make so many mistakes these days? 5/4 is equals to 0, right? And now this becomes lambda square. Minus 7/4 plus 2/4 is minus 5/4 lambda. And then 10 minus 7 is plus 3/8 is equals to 0. Multiply by 8, that gives 8 lambda square minus, okay, this is 10 lambda plus 3 is equals to 0. Okay, now what this Cayley-Hamilton theorem says is, well, okay, this exact characteristic equation is also this characteristic polynomial of a square matrix is also annihilating polynomial of that square matrix. Polynomial of that square matrix. Now how you can use this is, now what this means is, like, this equation, if I substitute, like, let's say lambda, this whatever variable it is, like, as the matrix itself, right? The matrix will annihilate to 0, right? So basically now this should be I over here, right, in place of 1. So okay, so this characteristic equation, like, if I substitute just a over there, like, the matrix, like, this whole thing just, like, just goes to 0. That just annihilates, means, I mean, like, just it just get destroyed to 0, right? So that's what Cayley-Hamilton theorem is. And this is actually pretty interesting theorem, right? We actually get an equation for a which reduces to 0, and that's actually a pretty interesting idea, and its proof is also pretty nice, right? Okay, so I guess now you guys, I know the idea about what this being annihilating means, and annihilating polynomial, and how to find that, right? There are also other polynomials, but yeah, but it just says that characteristic equation is also one of the annihilating polynomials, right? And from there we now get this relation between a square and I, right? Now what I can do is, now if I multiply both sides by a inverse, I get a square times a inverse minus 10a times a inverse plus 3i times a inverse is equals to 0 times a inverse, right? Now this becomes 8a minus 10i plus 3a inverse is equals to 0. Now I guess you guys have seen how to find a inverse, right? Now 3a inverse will just be 10i minus 8a So A inverse will just be 10 by 3 I minus 8 by 3A. Now we already know A, right? Our A. Let me get this down again. Let me get this down. Okay, so we're gonna find A inverse, right? Okay, we know that this I is just 1, 0, 0, 1, and minus 8 over 3. Our A is negative 1 over 2, 1 over 2, minus 5 over 2, 7 over 4, right? Okay, let's see. This becomes 10 over 3, 0, 0, 10 over 3, and then plus this is 4 over 3 minus 4 over 3, and this becomes 40 over 6, which is 20 over 3. Yeah. And the next one is minus 14 over 3. Yeah. Okay. Now if I add them, I will get 14 over 3 minus 4 over 3, 20 over 3, negative 4 over 3. So you see, I exactly got the inverse we were required to get. So this is how the Cayley-Hamilton theorem is helpful to find inverse, right? And this is actually pretty powerful because let's say if you go into 3 into 3 or 4 into 4, it's actually pretty hard to find inverse, right? But using this, find determinant will not be as hard as finding inverse. And then after you find determinant, like you just get it using doing some sums and multiplications. So I think this one is pretty powerful. Yeah, and let's go. Last one is also pretty interesting. Using Neumann-Series, right? Neumann-Series is actually okay. Neumann-Series is actually matrix power series, right? Okay, matrix power series, right? Now the thing is, you can actually write A inverse as this infinite polynomial. I'll give the reason why. This infinite polynomial from k equals to, let me write n, from n equals to 0 to infinity of I minus a to the power n. If this modulus of I minus a is less than 1, right? Just like this is a geometric series. Like for geometric series, we need the common ratio to be less than 1, right? So it's the same thing. And over here, we actually use the 2 norm, right? And 2 norm, like for any matrix, if it's a random rectangular matrix or any matrix, right? We then define it as the square root of like lambda max, right? Of this M transpose matrix, right? But if like M is a square matrix, then basically M and M transpose will have same lambda values, right? So basically, for a square matrix, what you can just say is like it will just be like the absolute value of the lambda max of the square matrix M. Yeah, okay. So that's the thing, right? And then yeah, over here, so basically this I minus a need to have like all the eigenvalues less than 1, and then if that's the case, you can actually use this formula, right? So yeah, okay, now let me say something. Like I told this initial matrix says that its eigenvalues are half and 1 over 4, which are both less than 1, and so that's why we will be able to use this technique. Okay, so yeah, let me again write this thing. And also, I told you I'll actually give you the idea why this works, right? So this work like this it's proof is same as the geometry series actually. Okay, so we have sum from n equals to 0 to infinity of I minus a to the power n, right? So you can use the formula a by 1 minus r. So our first term is I minus a to the power 0, right? By 1 is basically I in matrix minus r is I minus a, right? So I minus a to the power 0 is just I divided by this is I minus I plus a. I cancels out and this becomes I over a, which is a inverse, which is basically I times a inverse, and that becomes a inverse, right? Yeah. So it's actually interesting to see that this powers like this infinite series formula, it's also used here, right? It's actually used everywhere. Matrix is just as common as numbers. Okay. Okay. So now let's do that. Now, like I have already done it for you guys. The I minus a in this case will be I minus a basically. Okay, I can do this, actually do this right now. So 1 0 0 1 minus minus half, negative 5 over 2, 7 over 4, right? If you do the calculations, this turns out to be 3 over 2 minus half, 5 over 2, negative 3 over 4, right? Now, after you have I minus a, to actually find the nth power, for any matrix M, okay, let me just give the slight idea now what to do. To actually find the mth power, where's right over here, of a matrix like M, what you first do is you first break down M into this form P D P inverse, where P is in like orthogonal matrix. I mean, P is actually a matrix of eigenvectors, right? So it might not be. I'm not sure. Okay, basically P is the matrix of eigenvectors, and D is the matrix of eigenvalues. So basically, if let's say M has eigenvalue lambda with eigenvector B1 and eigenvalue lambda 2 with eigenvector B2, P is just this B1 vector, then B2 vector, right? And now D is like lambda 1, 0, 0, lambda 2, okay? And then this P inverse is just the inverse of this matrix B1, B2 inverse, right? And this is actually a matrix because B1 has two entries, right? B2 has also two entries. So okay. So this is how you first of all diagonalize a matrix, right? I mean, it should be diagonalizable to find nth power. I mean, yeah, there are also like other ways, but yeah, let's just talk about like a diagonalizable matrix. And then to find nth power, okay. So what happens is, now let's say if you are finding second power, so you will have PDP inverse, PDP inverse, right? Now P inverse P cancels, becomes I, so this becomes PD square P inverse. Similarly, like if you just continue, like our PDP inverse to the power n, uh, to the power nth power will just be PD to the power n P inverse, right? So, and now why this is helpful is because for a diagonal matrix, like let's say, again, let's say let lambda 1, 0, 0, lambda 2, for diagonal matrix, the nth power can be easily found out because this is just lambda 1 to the power n, 0, 0, lambda 2 to the power n. So this is how finding nth power is possible using diagonalization. Yeah, so that's what we're going to use here. I have already found eigenvalues, eigenvector, and diagonalized this, right? So this matrix I minus a will be diagonalized as, just save the time, 1, 2, 2, 5, right? And then 1, 2, 2, 5, and then it will be, I already told you eigenvalues were half and 1 over 4, so that they were less than 1. And then 5, this is the inverse of the first P matrix, 5 minus 2 minus 2, 1. Okay, so yeah, this is already in the form, right? And now let's do the sum, right? So now A inverse will just be sum going from n equals to 0 to infinity of I minus a to the power n, right? Now I already told you that if I take the nth power, what will happen is just the D, the middle matrix will have the nth power, right? I already told you that. And yeah, that's what the like advantage of diagonalizing is. And now this first matrix is just constant. I can take that out of the sum, right? That's just constant. And then I have this sum, right? Now I already told you that if a diagonal matrix has power n, that's just come to the diagonal elements, right? Yeah. And then again, this last matrix is also constant, so that goes out of the sum, right? Now after this, since we are summing all the like matrix, infinite matrix, right? What you can do is you can actually, this is same as just summing of the summing of the entries, right? Because like the sum of matrix like happens element by element, like one element with the corresponding element, right? So yeah, this is just a summing of all these corresponding elements. Sum of 0 is just 0, sum of 0 is just 0, and then this becomes sum from n equals to 0 to infinity of 1 over 4 to the power n, right? And then 5 minus 2 minus 2, 1. And now this is just geometric series, right? So now this is, it's easy to sum up. So 1, 2, 2, 5, and now this becomes a by 1 minus r. A by 1 minus r is half, 0, 0. Also here also a is 1, 1 by 1 minus 1 over 4, right? And this becomes, this has 5 minus 2 minus 2, 1. Okay. Yeah, now after that, this will be 1, 2, 2, 5, and then this one will just be 1 by half, which is 2, 0, 0, 1 by 3/4, which is 4 over 3, right? and then 5 minus 2 minus 2, 1. Now if you multiply the last two, what we will get is 1, 2, 2, 5, and this will be this 10, and then minus 4, right? And then you will have minus 8 over 3, and then 4 over 3. Yeah, 4 over 3. Hey, let me check. Minus 8 over 3, 4 over 3, and then 10, and then minus 4. Yeah, okay, now after that, what I can do is just multiply the first these two matrices, which is 10 minus 16 over 3, which is 30 minus 16, 30 minus 16 divided by 3, which is 14 over 3. And then this next is negative 4 plus 8 over 3, which is minus 12 plus 8, which is minus 4 over 3. Right, and then this is 20 minus 40 over 3, 60 minus 40 by 3, which is 20 by 3, right? And the last one is minus 8 plus 20 by 3, which is minus 25 plus 20 by 3, which is minus 4 by 3. So yeah, we get the inverse. I mean, this one is pretty interesting for me because you are doing infinite sum and you're getting the inverse, right? Like, this is so weird and good. I mean, so nice. And that actually gives us the inverse, right? 14 over 3 minus 4 over 3, 20 over 3 minus 4 over 3. And yeah, like this last one and second last one, it's just out of this world. Like, it's so good. What do I say? I didn't even have words to describe this. It's just brilliant. Okay, so I guess you guys now have new perspective of finding matrix inverse, like using the equations that relate matrix inverse with the matrix, right? And that new perspective is all you need. And there are also other ways. Do check them out. You can Google, you can ask ChatGPT, DeepSeek, or anything, and yeah, do get curious and search for them. So again, just to recap, the first one was using adjoint, which is just normal method, right? Second one was Gauss Theorem, where we placed a unit matrix next to the matrix and did draw operation to reduce first matrix to unit matrix when the second matrix transformed itself into the inverse, right? And third one was we first found our characteristic equation and told that even the matrix satisfies that characteristic equation, and then multiplied both sides by inverse, and then like we isolated the matrix inverse and found the matrix inverse, right? And the last one was using Neumann-Series, where basically we just used the geometric series formula, which basically proves this formula, right? And then we actually like had to make sure that I minus a has the like 2 norm less than 1, and then after that we just first of all we diagonalized I minus a so as to find the nth power, because otherwise it's so hard to find the nth power, right? And then after we diagonalized and found the nth power, just summed it up using infinite series again, using the infinite series formula, and that gave us the inverse, and that was so beautiful. So that was it, guys. Now I hope you are clear about all of this thing: Neumann-Series, Cayley-Hamilton theorem, Gauss-Jordan method, and adjoint of a matrix. So that was it. I hope you enjoyed this video, and if you found this beautiful, do share with the friends. Help everyone love this thing. That's the goal. And yeah, thanks for watching. I look forward to seeing you in the upcoming videos too.